Hello everyone, and welcome for this new session of our MATLAB tutorials. Now I will start talking about NMR simulation, and I hope to do a few sessions on this. Before starting, I would like to say that there are many softwares out there that are well optimized to do NMR simulation. For example, Spin Dynamica, Spinach, or Simpson, probably many others. And what I will show you is not how to use these softwares, but rather how to construct a simulation from scratch, which is probably not the most efficient way to get to the result, but it is, to my eyes, a good way to learn how to use quantum mechanics in NMR simulation. And for me, it has been very helpful to go really from the quantum mechanical definitions to MATLAB. I hope it will be useful to you too. Let's start with a little bit of theory and our plan for today. So we'll see how to simulate a 1D spectrum for a single spin half. And then we will move to a pair of J-coupled spins. For this, we will need the following tools. First, we need a density matrix that describes our system, and it will be our initial state. Then we need to be able to compute expectation values out of this density matrix. We need to define Hamiltonians that will drive our density matrix throughout time. And for this, we need also the propagator that will allow us to calculate the density matrix a long time under the effect of a given Hamiltonian. And finally, once we have propagated our Hamiltonian in time, we need to Fourier transform it to obtain a spectrum. We know that a spin in a magnetic field can be either parallel or anti-parallel with the field. Now I'm talking about a single spin half. And these two states, we will name them alpha and beta, correspond to eigenstates, stationary states, or also related to energy levels. But in general, the spin can be in a superposition of states. Here I write the function for the spin psi in the state psi as a linear combination of alpha and beta with two complex coefficients, C alpha and C beta. And throughout the whole presentation, I will assume that they are normalized, meaning that the sum of the square of their norms is equal to 1. Then you can use a vector representation of the spin state simply by writing the coefficients, and you don't write the whole alpha and beta, just the coefficients. So alpha becomes 1, 0, and beta becomes 0, 1. We'll need also the bras, which is the complex conjugate transpose of the ket. And for alpha and beta, because the coefficients are real, it's simply the transpose of the vector. Why is it useful to define a bras? In what we are going to do, it is useful because it allows to define the density matrix, which is the way we are going to describe in the simulation the spin state. The density matrix is the product of the bra and the ket, and the other way around, the ket and the bra. And then this horizontal bar at the top means that we take the ensemble average of this product. And you see here I've written what it gives when you calculate this product. And the fact that we have the ensemble average make the off-diagonal elements to average to 0. This means that normally a single spin has a phase, even when it's aligned with the field. But when you sum over a large number of spins aligned with the field, this phase factor vanishes because it's random in between all of them. So it is useful to use a density matrix precisely because we get rid of the phase factor, which is not useful in general in NMR. Then if you write for alpha and beta what the density matrix looks like, by taking this product, you simply get matrices with 1 and zeros for the rest of the coefficients. So let's go into MATLAB and write the density matrix for a single spin aligned with the field. That would be our initial state for the first simulation. So here I open a document. I will comment later on what I've already written in the document, but for now, let's just define our initial density matrix, rho 0. I write it like this. I run the code. You see rho 0 that has the shape that I have defined in the PowerPoint. Now, let's see how we compute expectation values. Here I've written the three angular momentum operators, Ix, Iy, and Iz. And on the right, the angular momentum operator vector, where the three vectors are together, the three operators are together forming a vector. And these operators will allow us to compute the expectation values out of the density matrix. For this, we used this formula, where we take the trace of the product of the density matrix with the operator. The trace is defined here on the right. It's the sum of the diagonal elements of the matrix. And an important property of the trace is that you can move the multiplication within the trace and give the same results. You may notice that it's divided by the trace of the density matrix, and it does not need to be the case because if we assume that we have defined our density matrix so that the trace is 1, which means that the state is described by a normalized wave function, then it's to compute the expectation value is slightly easier. And this, in my case, because I have defined the density matrix with a trace of 1, I will not write always divided by the density matrix. For example, during the FID that we will simulate, the signal along X, I assume that it's equal to the expectation value. If we want to be more rigorous, we can add proportionality factors, because of course what we measure is a current, it's not an expectation value directly. But for simplicity, I simply write that the signal I record is the expectation value of X, and then it's simply trace the product of the density matrix with the angular momentum operator. Let's apply this definition to our density matrix. So, for example, so before I do it, for this I will use what I have defined here. I've defined the angular momentum operators. For example, let's have a look at this one. So Iz is 1/2 and minus 1/2. I've defined all of them, and you might notice that instead of writing I for the complex number, I've defined AI, being square root of -1. Why is that? It's because I will very often use for loops of this shape. And I'm so used, like many people, to use the number I that I want to keep it for this. Otherwise, I had the problem in the past, I will make mistakes, and using this prevents me from making mistakes. So let's calculate the angular momentum in the 3 direction for this density matrix. In MATLAB, to compute the trace, you simply write trace. And if I want the angular momentum along Z, I write it like this. I run the code, and you see I get 0.5. I can do the same for X and Y. And just to display it in a nicer way, I'm going to use this. So this writes it a bit slightly differently, and I can add, I will convert it to a string that I can add here, Z, and written in this way. It gives me Z, which is the string here, and then the expectation value converted to a string. This way I can do the same with X and Y. I run the code now. Now you see that I have no angular momentum along X and no angular momentum along Y. Just going to add this node before closing. Yeah. Okay, so we are now able to compute the expectation value. That's a good thing. Now let's go back to some more definitions. We now need to define the Hamiltonian of our system. The general Hamiltonian for a single spin in a magnetic field is given here, where B is the field vector and mu is the magnetic moment of the spin. And I beg your pardon if there are some sign mistakes in my slides. I did my best, but and I try to be consistent. It's possible that at some point I have a sign mistake. Please let me know if you notice one. So if we rewrite the angular momentum, the magnetic moment as a function of the angular momentum, we have the reduced Planck constant h bar that appears with the magnetogeric ratio of the spin. And we can now take the dot product of the field vector and the angular momentum operator. And here is the result. And we can finally rewrite it, taking minus gamma b being the nutation frequency or Larmor frequency. So this is the general Hamiltonian. Now if we write it for free evolution, when there's only the magnetic field along Z and no radio frequency pulse, then Bx and By are 0. So we only have the component along Z. And we call it B0 by convention, with the Larmor frequency omega 0 being minus gamma B0. During the pulse, assuming that I neglect the effective free evolution during the pulse, here's Hamiltonian I get, where I only have the radio frequency pulse with B1 with nutation frequency omega 1. Let's go back to MATLAB and write these two Hamiltonians. For free evolution, I take Iz, and I need to give it a frequency. I will define here the frequency. Let's start saying that it's 10 Hertz. And I will write it as it's 10 Hertz, but I want to convert it into radians per second. So this is simply my Hamiltonian for free evolution. Now for the pulse, assume that I have a B1 radio frequency pulse of 30 kilohertz, again in radians per second. Yeah. So H1 is then given by Iy. So I assume that I pulse along Y. So here I have defined my two Hamiltonians for the simulation. But to know how the Hamiltonian affects the density matrix, I will need the propagator. So let's see how we define it. This is the propagator for Hamiltonian H. It's and this exponential is not an exponential of a number, it's an exponential of a matrix. You see here the definition of the matrix exponential, and it's important to keep in mind that computing the matrix exponential takes time for the computer, so it is important to have it in mind when you code, to try to have to calculate it as not too often if it's possible to avoid it. Here is a sandwich formula that tells you the density operator as a function of time. When you start with a density matrix rho 0, to calculate it along time, you flank it by the propagator. On the right is the propagator, and on the left it's the inverse of the propagator. That is computed this way. The propagator has a math property. It's unitary. So to have the inverse, we can simply take the complex conjugate transpose, which is faster to compute than to recalculate it. Finally, I would like to make a comment on this that is very important, is that we may get rid of the reduced Planck constant everywhere, because in the Hamiltonian you always have h bar, and in the propagator it's divided by h bar. So instead of writing h bar and then dividing, we simply get rid of it everywhere, and it will make life easier. So Here, when I wrote my Hamiltonian, I did not make the comment. In fact, I did not write h bar precisely because I want to write my Hamiltonian in this modified way for simplicity. For the free evolution, the Hamiltonian will look like this. Here I have simply replaced h by h0. And for the propagation of the pulse, I've replaced h by h1. I've written u0 of t and u1 of tau. Why is that? It's because for the pulse, I just want to calculate the propagation at the end of the pulse, meaning I want to know the effect of the pulse. I don't care of what happens during the pulse. I will just calculate it for tau, which is the pulse length, while for free evolution, I will calculate it a long time during the FID. And here beta is the pulse angle that the propagation achieves. And to know the pulse length, once I have defined omega 1, I divide beta on both sides, on both sides, and I get beta divided by O1, which is what I'm going to do now, is to define the time of my pulse has to be omega 1 divided, pi over 2, which is the pulse angle that I want to achieve, divided by omega 1. If I run this code, you see I have a pulse of 8 microseconds because I have chosen a mutation frequency that is kind of typical for liquid state. Okay, so now that I have my time for the pulse, I want to calculate the propagator, or this propagator here, for the pulse. So U1, the propagator of the pulse, will be the matrix exponential of minus the complex number I, H1, and tau p. I want to raise your attention here. This is very important. I'm not writing exponential like this. I'm writing exponential with the M so that MATLAB understands I'm computing the matrix exponential, which is not the same as the exponential. If you write the exponential simply with exp, it will compute number by number in the matrix, and so it will give completely wrong results. Now that I have my propagator for the pulse, I can calculate the density matrix after the pulse by using the sandwich formula. Here what I have written is row 0, my initial density matrix, where the spin is polarized along Z, and I flank it by the propagator U1. This here computes the transpose complex conjugate. This is what I explained you earlier. To compute the inverse, I can calculate the transpose complex conjugate, which is much faster. So this, in principle, row 1 should be the density matrix after pulsing. So let's copy this code to compare after pulsing. So here, if I want to compute the expectation value along x of row 1, I just have to replace here. And let's run the code. So what do we see? Before pulsing, we had 0, 0, 0.5, and minus. Now we have minus 0.5, 0, and some number, very small. Why do we get some small number and not 0? It's because the computation of the number is not completely perfect. It's supposed to go to 0, but there's some because it's numerical and not analytical. There's some mistake in the calculation. If I really want to get rid of this, I can, for example, round. For example, the fifth digit, and now if I just round to the fifth digit, this gives me 0. Now I have row 1 is my density matrix after the pulse, To simulate the spectrum, what I need now is to do the FID. So I'm going to define parameters for my FID, saying, for example, that the acquisition will be during 5 seconds. I want a spectral window of 100 Hertz. My frequency is 10 Hertz, so 100 Hertz will be sufficient. And to calculate the number of points of my FID to reach this spectral window, here is what I need to do. So this will work, but I would prefer to have a number that is a power of 2, because it's faster for the Fourier transform, and it's also the way it works in topspin. And this formula here, I won't comment it too much, but this gives me the closest power of 2 of this number here. Let's compute it. So it gives us a FID of 512 points. I will now create a loop, a for loop, where I will calculate the expectation values of the density matrix a long time during my FID. So I need to create a time axis. I have already used in the previous sessions this function linspace. But this creates a vector that with numbers that start at 0, end up at AC, and have endpoints. It will be my time axis during the FID. Then I need to create empty vectors where I will write my expectation values. So this is a signal along x during time, sxt. It needs to have endpoints and n elements. So this is n rows and 1 column. And same thing along y. Now that I have this, I can define my for loop. So I remind you that when I write this, it means that the code that I'm going to write in between the for and the end will be run from 1 with n times in this case, with I taking values from 1 to n. In each of these iterations, I want to calculate the propagator U0t. Why do I call it this way? Because it's the propagator U0 is for the free evolution Hamiltonian, H0, and T because it will depend on time. So just my way to make it clear. And I use the same way to write it. But in this case, it's this time that varies, and it's not H1, it's not the plus Hamiltonian, it's the free evolution Hamiltonian. I can now calculate the density matrix as a function of time using the same expression as here. I just need to replace it. Now it's no longer U1, it's U0t. And my density matrix that I'm propagating is not row 0, it's row 1. It's the density matrix after the pulse. If I run this code, what will happen is that I will, for each of this iteration, it will overwrite row of t. So I now need to compute the expectation value as a function of time. And for this, I use the same as earlier here. Row t. So this calculation here, it will calculate for sxt. So at position I, it will store the expectation value of the angular momentum along x for the density matrix along time. There's something that it's you don't know until you do the mistake, is that this number, although in theory it should be real, sometimes there are some remaining imaginary component for the same reason that here we had a non-zero element along z, although we should have it should be 0, because of the imprecision of the numerical calculations, at some point it might become complex, and this will cause problem in our later on. So I only take the real part, and so that the vector is only complex, contains real numbers. And I do the same for y. So now this loop completely calculates the FID with endpoints. And to show you the results, I'm going to plot the signal along x as a function of time and the signal along y as a function of time. Let's run the code and see if it works. Yeah. So what we see here is the acquisition during 5 seconds. The signal oscillates from minus 0.5 to plus 0.5. And as we could expect, we have the two signals along x and y, which are in antiphase. One is a sine and the other one is a cosine. Since I haven't implemented any relaxation in my model, I've just assumed that the transformation is unitary at all time. The signal is not decaying. And I cannot take the Fourier transform of the signal like this, otherwise I will have artifacts. So at the moment I will take the Fourier transform, I will have to add some line broadening, meaning that I apply a window on my signal so that it decays. I will use a simple mono exponential with a line broadening parameter. To do this, I will use a homemade function that will signal 1D. And I don't want to go too much in details of this function. Basically, it computes the Fourier transform of the signal. Because I'm not so, I don't master well the Fourier transform, I will just explain how it works, but not go in the details. Just explain how you can use it rather than how it works in detail. So you first have to give the time axis, and then you have to give the signal that you want to Fourier transform, but you have to give it in complex form. Here we assume that we have quadrature detection, meaning that we detect both along x and y. So what I've written here takes the sum of x, the signal along x and the signal along t, but I have multiplied it by the complex number I, which means that for each point of time, I now have a complex number representing the signal in the complex plane. So it's a equivalent way to write it. There are a few options in this function. So if I want to add line broadening, I write the option LB, and I'm going to ask to have like 1 Hertz of line broadening. And if I want to display the spectrum, I have to add the option spectrum and give it the value true. And the same thing to display the FID. Now, if I run this code, let's see what happens. Okay, let's start with the FID. So here you see the same FID as earlier, but now we have this this window that is applied to it to make it decay. And concerning the signal itself, not surprisingly, it's negative because in the way I have had pulsed, the value just after the pulse was negative on x, so the signal is indeed negative. And in the function that I've created here, you can choose a phase as well. So you say option, phi, pH for phase, and here if I write pi, it will change the phase of the signal. Just to show you another example, if I want now, if I put, for example, instead of 10 Hertz, I put minus 20 Hertz. It appears here, so our simulation does the job as we expected. There's something I did not know before I started doing simulation, but some of you may know it well, what happens if I set the frequency to be out of this window? So for example, if I put 60 Hertz. So I put 60 Hertz, but it's back inside the window. And this is what we call refolding. Very often when we do 1D experiments experimentally, we don't have this problem because outside of the window, most of the time we are also outside of the, we might be outside of the detection range of the probe. So we don't have this problem. But in here, where we don't have a Q factor, we can easily have this refolding problem. So we have to be careful of when we see a signal, it might be just that we have badly, so we think, oh, well, I have something resonating at 42 Hertz. But in fact, it's just out of the window. Something else that I would like to add is that in my function, so here you see a bit of zero filling would be useful. So it's also implemented in this function. If I type 0 for zero filling, then I have to give the numbers of zero filling I want. So my number of points earlier was n. So by writing this, I multiply the number of points by 16. And now I have a better result signal. So now we have completely calculated our 1D spectrum, but we were using a frequency in the order of tens of hertz, which is not what we have in real NMR experiments. This would it could be right if we assume that we are in the rotating frame. But what I would like to do now is simply to write the same thing, but in the lab frame. It will not change much, but it's important to do it. So in the lab frame. Now I'm going to define a carrier frequency and a chemical shift. I assume that I'm looking at proton at 400 megahertz, for example. And let's say that I have a chemical shift of 1.5 ppm. Oh, I forgot to write the carrier frequency in radian percent. And I will define my Larmor frequency as a function of the carrier frequency. Of course, here I'm confusing two concepts, which are the reference frequency and the carrier frequency. Of course, I could define both, but just for simplicity, I only define one. Because it's not so interesting for a simulation. So now the whole code will be the same, it's just that it will assume that the spin are processing at a frequency in the order of 400 megahertz. With what I have told you earlier, I will obviously see, if I just run the code like this, I will see a signal that appears somewhere in the window, but in this case at 20 hertz, although it was oscillating at 400 megahertz. The reason is this refolding. So I have implemented in the function here the option 01 for carrier frequency. And I have to give it, so here I set the option 01 to the value 01 that I have defined here. And the function signal 1D will mix the FID with this carrier frequency and in the same way as it works in a NMR preamplifier. Now I run the code. So it gives me 30 hertz. And I will also change a parameter to make it clearer. FID. I don't want to see FID anymore. I can write it, I can change the units in the function. So I write unit ppm to have it in ppm. Oh, there's a mistake. I forgot the comma. And I have a mistake. It's supposed to appear at, oh yes. So my mistake here is that I have not changed the spectral window. So I want to have a much wider spectral window. It had only 100 Hertz with here. So let's put, for example, 3 kilohertz and run the code. Okay, I can make it a little narrower. 3. Okay, now it's surprising, but because my signal still doesn't appear at 1.5 ppm as it should, I have defined here. So my chemical shift is 1.5 ppm, and here my Lamo frequency is defined properly. Just gonna compare. I'm comparing with a simulation I had done earlier, which is supposed to be the same, more or less. Let's see if we put the chemical shift to 0, if the frequency appears as it should at 0. It does not. I must have done some mistake somewhere. Sorry for that. I will correct the code before I put it online to make sure that it calculates what it should. It's surprising. Yeah, I don't know what happens. I must have forgotten a factor 2 pi somewhere, probably. Anyway, I will correct it before I put it online. Before we take a break, I would like to do the same calculation that we did in numerically. I would just want you to show. I want to show you how you can calculate it analytically, because I think it's quite instructive. So I will rapidly show you two calculations. One is the propagation of during free evolution of a spin aligned with the field, and then a field in superposition of states. So here I take the Hamiltonian of the free evolution and the density matrix of the spin aligned with the field. When I calculate the sandwich formula. In the middle, you see here this 1, 0, 0, 0, which is the density matrix of the spin aligned with the field. And it is flanked by the propagator of the Hamiltonian, which I have calculated manually. And when you make the matrix multiplication, what you find out is that you were starting with row 0 and you end up with row 0, which means that the density matrix is invariant under the effect of this propagator. This is what we expected. The spin is supposed to be stationary when it's in a population along the field. Now, if we compute as we did earlier, the expectation value, we get 1/2 along z and 0 along x and y. Let's do the same thing, but starting with a density matrix, which is not a pure state, but a superposition of state. Here, the state I've written, which is the sum of alpha and beta with a normalization factor in the front, is the wave function when the spin is aligned along x. If I write as before the sandwich formula, in the middle you see this matrix is 1, 1, 1, 1, which is the density matrix for the spin aligned along x. And you take the sandwich formula, you make the matrix multiplication, you get this this matrix on the right that depends on time, where the off-diagonal elements depend on time. Now, when you compute the expectation values, you just need to do a little bit of trigonometry, and you will get a cosine for x and a sine for y. So they depend on time, and this is really our FID. We have no expectation value of the angular momentum along Z, and we have an oscillation in X and Y. This is our recorded signal. Okay. And we can represent it as using a vector model in this case. The red arrow is the field, and the blue arrow is the magnetization. And it means that the magnetization is turning around, processing around the field in the XY plane. I think it's a good point to take a break. And after the break, we'll move on with some more details about the density matrix, and then we'll move on with the two-spin system. So let's have a break now.